Yes, sir.
All right. Okay, we'll start now. All right, welcome everyone. My name is James Deeney. I am this year's chair for SEI Philly. Please take a moment to review this slide. As with any virtual meeting, whether it's Teams, Zoom, or WebEx, please remember to keep yourself on mute at all times. Also note that this meeting will be recorded and the link to the recorded event will be provided at a later date. During this presentation, if you have any questions or comments, please write them in the chat window for the speakers to address at the end of the presentation. I understand that many of us have meetings that bookend this 1 hour time slot, so we will try to honor this time commitment, but if we run a little over, again, please bear with us. So officially, welcome everyone to SEI Philly's February 2021 Technical Lunchtime Webinar. I want to thank everyone for joining us today for a great presentation by Joe Sullivan and Sean Larby from WSP. We have close to 100 people registered for this event. And again, another great turnout. And for those that are in attendance on this call, we will email a link so that you can download the PDH at a later date. Before we introduce Joe and Asin, I do want to recognize this year's board. They are myself, James Deeney as chair, James Greco as vice chair, Jack Cardinal as treasurer, Nikki Eno as secretary, Keith Murrow as program director, Michael Urban as director of public relations, Colin Drager as Deputy Director of Public Relations, and Dan Cush is our past chair. So with that, I'd like to introduce today's speakers. Joe Sullivan is a registered PE in Pennsylvania, New Jersey, and Georgia, and a project manager at WSP with over 30 years of design and construction experience. He obtained his bachelor's from Temple University. Welcome, Joe. And Sean Larby is a registered PE in Pennsylvania, Virginia, Washington, D.C., and a few other states, probably about 4 or 5, I think. He is a senior structural engineer and lead design engineer for the Junction Viaduct Rehabilitation project at WSP, and he obtained his master's and doctorate degrees from Drexel University. And welcome, Sean. So with this, gentlemen, the floor is yours.
All right, Sean will take over. All right, thank you.
My screen.
I can see your screen. Thank you, Asin. And thank ASC SEI for allowing us to present this project. We did the project for PennDOT District 6, but since it was a multi-span steel structure, there was oversight from PennDOT Central Office. The project is out in construction now. We're through stage 1 and into stage 2. It's a $90 million construction project, and it is being constructed by South State Construction. I'm Joe Sullivan. I was the project manager, and Sean Larby was the lead structural engineer, and we'll try to keep this structure focused since this is the Structure Engineer Institute. Next. Just an overview of what we'll go over today. I'll go over some bridge stats, the goals of the rehab, and the construction staging, and then Asin will cover the sequencing for the pin and hanger elimination, the bearing replacements, the fixity changes within the bridge, and the joint reconstruction. Next. Okay, just some quick bridge stats. If you're not familiar with the Roosevelt Expressway, it is between I-76 and the Roosevelt Boulevard. It's limited access highway. The project is right before you go underneath the Broad Street Tunnel. The dominant feature that it crosses is SEPTA's regional rail line. There's main line tracks that go through there, but there's also, as you can see on the left side there, a large yard, at least I could see. The SEPTA Wayne Junction yard is on the left side. After that, as you go further north, it goes into the neighborhood of Nicetown, and it's over local roads. It's very obviously close in quarters there with the neighbors. You can see on the northbound side, the bridge is paved with bituminous, but on the southbound side, it's not. So that's what kind of led to this rehabilitation. Go ahead, next. The bridge itself is 2,500 feet long. It's a 15-span multi-girder viaduct built in 1956, carries 120,000 vehicles a day. 3 lanes southbound, 2 lanes northbound, but the 3rd lane southbound begins with the on-ramp right at the north end of the bridge. It's really the Broad Street on-ramp, but it really comes off of Cayuga Street, a collector distributor road. And we were able to eliminate that, close that on-ramp during construction because there's no shoulders on the bridge. So that really opened up some area for construction. It's a riveted high-strength build-up girder, high strength for its time, high-strength steel for its time, wouldn't be high-strength steel for this time, with pin and hangers to make the bridge determinate. In 1981, the deck was replaced half with precast panels and half with cast in place. The northbound has the precast panels. That's the one I showed you, has the bituminous overlay. That was a value engineering a proposal from the contractor. Apparently did not go well in the construction phase. So when he went to the southbound side, he used the cast in place decking. 92, there was a rehab, and the overall MBS condition rating for the bridge was poor for this rehabilitation for deck, superstructure, and substructure. The bridge has many joints, and that's the main problem. It's the water infiltration through these joints, its impact on the pin and hangers, its impact on the bearings and the piers. The northbound side that was overlaid, they literally just overlaid the pin and hanger joints which were plate dams. So there was constant water infiltration there. And on the southbound side, they did try to do a deck rehabilitation, but they were more like temporary joints with elastomeric concrete that just did not hold up. And you can see 100% infiltration. And we talked about the precast deck panels. So this is a close-up look. They're about 10 feet wide. They're 4-inch thick precast panels with a 4-inch thick topping slab. So it must have been soon after construction there was reflective cracking through that topping slab affected rideability. So they just paved over the northbound side, but they continued to wear at a bad rate. And you can see there's cracking on this little piece of coping that comes over the precast slab, and that was starting to fall off of the fascia side of the parapet and also at the median side. And here's a look underneath. You can see on the northbound side, you can see the precast panels, southbound side, the stay in place forms. But you note it is a curved girder bridge, but it's really not a curved girder. It's a kinked girder bridge. And this is one of the pin and hanger locations in the center there. You can see that, well, there's some netting there that was catching some of the falling concrete, but right adjacent to that is the pin and hanger location where the kinks occurred, and that had to be taken account for in the pin and hanger replacement. Drainage throughout the bridge was never replaced and really wasn't draining properly. It was just draining right onto the substructures. And on the bottom right, you can see what that ended up doing to the bearings and the steel at the bearing locations. So with an open joint above each pin and hangers being very critical, this is, essentially this is a suspended span. There's a cantilever section that comes off each end of the pier on each side, and it's a drop-in span, and that's all that's holding that drop-in span is that pin and hanger. And you can see what the years of water infiltration had done to these. Upper left is what happens when you have a bearing that's over top of a continuous and it's well protected and it's nice and dry. That's 60 years later and it still looks sound and really nice. But the ones that were at the open joints, these are all the double bearing open joints. Just the years of water infiltration and particularly the salt infiltration had just taken a toll on the bearings and pedestals. So the goals of the rehabilitation: eliminate the pin and hangers, which will reduce the number of joints on the bridge, replace the deck and the bearings, repair and paint all the steel superstructure, repair and protect the substructure units, and all while maintaining 2 lanes of traffic in each direction. So currently, or the existing, there was 16 joints on the bridge. The ones in black that you see there, they're the ones between the units. There's a 3-span unit to the bridge, a 7-span unit, then a 3-span unit. At the north end, there's 2 simple spans as the bridge splays out for the off and on ramps. The red lines are all the pin and hangers. So when the bridge is done, when the rehabilitation is complete, there'll just be 3 joints on the bridge between the units, and then at each abutment, the joint is moved to the end of the approach slab. So only 3 joints on the bridge. So how to get there. Here's the construction staging. Like I say, there's 5 lanes, 3 lanes southbound, 2 lanes northbound. There's literally like no shoulder on the bridge. So eliminating the one travel lane and only maintaining 2 lanes in each direction was key. So along the bottom, you see a pin and hanger P&H, and that just as you go through these stages, you'll see, even though there's some things you have that a scene will cover much better. The pin and hangers get replaced per stage. The bearings get replaced per bearing line. And then the difficulty with the pin and hanger replacement, the hatching, the cross hatching is the deck that gets replaced in the stage, but the X hatching is what area that needs to be opened up in addition, just at the pin and hanger locations to daylight the full pin and hanger. So they had to put a temporary diaphragm in and this little edge support beam to open up that full girder location to remove the pin and hanger location, put a drop-in section. So this is that. You see here, you can see the temporary diaphragms in place. There's an edge support beam there, and you actually can see the daylighted section where they just opened it up enough, about 15 feet, to drop in a new section of girder to splice to the existing girder and remove the pin and hanger. This is the current stage right now. If you're driving through there today, it's in stage 2 of construction. It's a split southbound stage, which is tough for the traveling public and also tough for the contractor with the 2 cattle chutes. But you'll see on the right side, now there's 3 pin and hangers that were eliminated there. And on the right side, they have to maintain that one diaphragm through the next couple stages because there's only a temporary piece of decking, and that's what they're driving on. They'll come back and do that in a later stage. This stage goes and continues on the southbound side with just the 1 pin and hanger being daylighted. And you'll notice they're using zone guard barrier. That the shape there is kind of correct. It's that steel zero deflection barrier is being used throughout. Next. So then stage 3, they'll go out and do the remaining part of the southbound side and do 2 more pin and hangers. And then we'll move back to do the northbound lanes, get rid of the piece of deck that was being temporarily supported and traveled on, and 1 more pin and hanger location. And then stage 5 will be the remaining portion of the deck. By that time, all the pin and hangers were replaced by that time. You'll see there's a lot of joints in the deck. You see every line that was maintained there. So there's going to be an epoxy based overlay when the bridge is completely done. And in this last stage, the other joint that's eliminated is the longitudinal joint down the complete bridge. The bridge is going to be made composite, first of all. It's a lightweight concrete deck to increase the live load rating. And the median barrier is you're going to hydro demo a little piece of the deck and tie the rebar to that and recast the median barrier. And then that would be fully completed construction. It's a couple of years, it's a year or more down the road, but so I'll turn it over to Asin now, I believe. And he'll go over the pin and hanger elimination process.
Thanks, Joe. So in this portion of the presentation, I'm going to focus on the pin and hanger elimination. So this includes not only the pin and hanger elimination, obviously, but also the changes of fixity when replacing the bearing, because all of the bearings are being replaced and the structure becoming continuous now doesn't need to have the bearing fixity that it used to have. It has to change. So these are the 3 major units of the bridge. Unit 1 is about 525 feet with a 3-span. Unit 2, 1,320 feet with 7 spans. Unit 3, in excess of 500 feet, 3-span. And Unit 4 is a 2 simple span, which we made continuous by joining the 2 spans at Pier 14. So if we look, for example, at Unit 1, what it was before and what it's gonna become. So you can see it's a 3-span, and you can see the fixity at the different substructure units. So because it's broken into pieces at the pin and hangers, so each piece has to have some sort of fixity to the substructure to anchor it. And you will notice also, because of that, some of the joints at the pin and hangers are either expansion or fixed. So you'll see in span 1 of unit 1, for example, you have an expansion pin and hanger. So the span can move with temperature there. So that's why it's fixed at the abutment. And the rest of it is fixed at pier 2. And so the entire cantilever span and the second suspended span are attached at the second pin and hanger joint. So that's fixed. So when this becomes continuous, obviously we want pier 2 to be fixed and the rest of the structure be expansion. So that's the change of fixity that has to happen. And we can see that in unit 2, which is the longest. Now for unit 2, because it's extremely long, we had to figure out how many piers actually need to be fixed. Ideally, you want to fix as little as possible if you can take all the lateral loads at that pier that you're fixing. But unfortunately, because it's it's 1,300 feet, so we had to fix 3 of them, and that was controlled by the seismic connection force. So we picked pier 5, 6, and 7 to be fixed. It's not exactly symmetric, but as close as we could get it. This is what happened at unit 3. Kind of similar to unit 1 because it's 3-span. However, what happened here is that we found that I guess pier 12, which used to be fixed, we found that pier 12 is not doesn't have a good capacity to provide the fixity we need. So we analyzed pier 11 and found that it was better. So we actually switched the fixity and decided to fix pier 11. Again, at unit 4, we just joined the 2 spans using a connection at pier 14. And so we used the continuity diaphragm, kind of like what you do with a pre-stressed beams. So we replaced the 2 lines of bearings with a single one using a bolster and tying, the bolster to the bottom flanges of the 2 girders. So as Joe mentioned earlier in the staging, the pin and hangers get eliminated and the girders spliced per stage. So for whatever width of deck, you have 2 or 3 girders at each time, sometimes just 1. But the bearings, anytime we replace bearings, they had to be done across the whole bearing line, simply because we want to maintain the same movement in the structure. So in order to do that, the equipment used by the contractor, for most of the bearings, we used jacking towers, as you can see in this picture. So because it's accessible for most of the length of the structure, so it was very easy to do. And these jacking towers include jacking boxes that allowed the contractor to be able to, once the structure is jacked at the pin and hanger, then, once it's shimmed at the proper elevation, then he can remove the jacks and use them elsewhere. That's another picture of the jacking box. Now, elsewhere where we couldn't jack from below, and this is mostly over the tracks at SEPTA and CSX, we designed a jacking frame or a strong back that went on top. So from atop the deck, again, at the pin and hanger, there's enough removal of deck so you can get in and do the splicing. So basically the jacking frame, all it does is just pick up the suspended span, which you see on the left side of this slide, through those rods, and that's where the jacks are placed. And then it reacts against the tip of the cantilever span, and then it's anchored in the back. So you have a downward reaction at the tip of the cantilever and an upward reaction in the back. So that's how the suspended span gets picked up a little bit, enough to remove the load from the pin and hanger, and then remove it. And so we cut out an entire piece of girder, basically the entire area where there's so many rivets, and it was the quickest thing to do rather than just splicing directly through those rivet locations. And that's what the strong back or jacking frame looks like. You can see the pieces of the girders that were cut out of there. Another device that we made use of is a bearing lock. So this is, in some cases, it happened in one location where we had to switch the fixity of the bearing. So we designed an expansion bearing for the final condition, but temporarily during construction, it had to remain fixed. So we would lock it, and then when it's time to switch it to expansion, we'll just remove the lock. We also made use of thrust plates. These are already existing in the existing structure at those fixed pin and hangers. That's how the movement is transmitted between the suspended span and the cantilever span. But in some cases, before we move into replace a pin and hanger to make the girder continuous, so at that line of girders, we would introduce these thrust plates all across the structure, all 9 girders. And then we'll go back into, say, the 2 or 3 girders that need to be spliced. We'll remove the thrust plates and put the splice there. So that's how we maintain that compatibility in the movements. Joe talked already about the drop-in section. So this is the section and girder that we put in to replace the pin and hanger area. So we cut out pieces from either side of the pin and hanger and insert a new piece there and splice it on either side. And at the center of that section, there's a connection plate to put in a cross frame. So where there used to be 2 cross frames on either side of the joint, now it's going to be just 1 cross frame, and it so happens to be at the kink, which is that's where the pin and hangers were located. So we paid a little more attention to the cross frame as it's transmitting some of the lateral effects from the curvature of the bridge. This is another view of the drop-in section. As you can see, because of the kinks, these drop-in sections were slightly curved to, to make to transition from one girder to the other because of the kink. And for making these girder continuous, we had to establish certain principles to follow at any step to make sure that we don't introduce too much locked-in stresses in the structure. It's a very complex undertaking because it's being done in stages. Ideally, you would just close one direction and do the other, but unfortunately, we couldn't do it here. So there's an incompatibility of behavior on the side that's being made continuous and the side that's still hinged. But at least for temperature movements, we had to make sure that they moved the same way. So the first principle, as you can see here, was the idea to maintain sufficient anchorage to the substructure because of we're making the structure continuous little by little. Therefore, at any stage, we have to have enough fixity so that the structure is anchored well to the substructure. Maintain compatibility of movements, as I explained before, and also make sure that the joints, as the structure gets longer, continuous, the joints have enough opening to allow for temperature movement in the construction, during construction. And finally, in certain places, we had to enforce a temperature restriction when we're splicing. We'll get to that in a minute. So just to go through the steps, I'll give you the example of Unit 2, and all the units are done kind of in a similar way. So here's Unit 2, starting out with what you see on the screen here, 7 spans, and the pattern of expansion of fixity that I've talked about a little bit earlier. So in stage 1, which was the 3 girders, 4, 5, and 6 that are in the middle, the first thing that was done was to go to pier 10, which is the end of Unit 2, and replace all the existing bearings. As you can see before that, pier 10 south is expansion, pier 10 north is fixed on Unit 3. The contractor made the decision to start from the north side. So actually, Unit 3 would have been done already. But when you get to pier 10, those bearings obviously had to be replaced all together at the same time. Because you jack both sides of the structure and you go at it and work your way. So we replaced pier 10, expansion both sides. And then we went to pier 8, and that pier 8 is expansion, so it gets replaced with expansion. That's not a problem. But then when we went to pier 9, it's fixed, and in the future it's going to be expansion. So we had to replace it with an expansion bearing that will be temporarily fixed. So we used that bearing lock at this location. In the next sequence, we removed a portion of the deck in span 10, and then we replaced or we eliminated the pin and hanger in that span. So you can see at any step, we're still maintaining the fixity that we need. And in the last step here, we went to span 4 and introduced a thrust plate to tie the suspended span in span 4 to tie it back, and then go and replace the bearings that used to be fixed at pier 3 with expansion bearings. In these couple of steps, the next thing that was done is go at each location in Unit 2 where there's a pin and hanger, remove enough deck, place the temporary deck support we showed you earlier, do the temporary bracing, and remove the deck over the entire area. So then the contractor decided that he wanted to replace one of the bearings at, I guess this is pier 6, which used to be expansion. Now it's going to be fixed. So in this case, we had to introduce a temperature restriction because these are consecutively fixed piers. And so either the contractor would have to jack the pier to get to the proper girder length at whatever temperature that day, or wait until a certain temperature that we provided to the contractor is reached. In other words, we gave him a bracket between 50, plus or minus 15 from the 68-degree temperature, which we thought, that bracket is small enough so that the locked-in stresses are not going to be huge. So in this case, the contractor decided to wait a couple days and hit the target temperature and just fix that bearing. In the next step, we introduce, we do the pin and hanger elimination in span 8. Again, we maintain enough fixity everywhere. And in the next step, we go to span 6 south, just like span 8 south and span 6 south. We come back to span 8 to introduce the thrust plate in advance of removing the pin and hanger. So the thrust plate would be installed across all the structure, so for all the 9 girders. And then we start replacing, removing the pin and hanger at the same time, unlocking the bearing at Pier 9, which used to be temporarily fixed. And so in the next step, then we go and do pin and hanger elimination at span 8 north. And in the next step, we switch to span 6 north, but because now we're tying these 2 big sections, then there has to be temperature restriction for the installation of those thrust plates. So next step, we introduce the continuity in span 6 north. And in the next one, we go to span 4. Span 4 already had the thrust plates, so we tie that in there again. And final step is to pour the deck and install the joints. There's one spot that I missed to talk about, and that's where we had to make sure at some point we had to go and open the joints at the ends of this unit. So for the subsequent stages, we essentially repeat what was done, except now all the bearings have been replaced, and all we need to worry about is just repeat the same sequence, observing temperature restriction when they apply, etc. In the last stage, as mentioned earlier, we shift traffic to the sides and do the median and install the overlay. That concludes this portion of the presentation, and thank you, and we'll open this to questions if you have any questions. Thanks.
If anybody has any questions, feel free to add it in the meeting chat. Just give it a minute in case somebody's typing. First question, what type of joints were used? Modular or tooth?
Modular dams, yes. We used modular dams at 3 locations, just between the units, basically. Elsewhere, we, off of the bridge, we used strip seals.
What software was used to analyze the piers?
At the time we used PA Pier because this was a while back. That software is no longer supported, I believe, but that's what we used.
Were link slabs considered to join the two simple spans?
Not really, because we're replacing the deck completely. So in order to avoid doing a full splice of the girders, we just decided to do a simple for dead and continuous for live load. So we kind of copied the detail that PennDOT uses for pre-stressed beams. We introduced the compression wedge at the bottom flange and carried the live loads with a continuity reinforcement in the deck.
Another question, did the cast in place deck hold up better than the precast deck?
Yes, the cast in place deck was in much better shape. Like I said, the precast deck from the time as long as I can remember, that it was overlaid because of poor rideability, and because there was a 4-inch, it was 4-inch precast with a 4-inch topping slab. And I think it was the reflective cracking because of differential movement between the precast deck slabs must have been causing poor rideability, and so they just paved it over. It's been paved over for more than 20 years that I know of.
Did those joints open up or was it just more reflective cracking?
I wasn't sure. I never saw it without the paving on it. So that's how long it's been paved. So it was paved over within 15 years of it being placed. I think that I could probably find out when it was paved, but
You're not selling precast decks there.
yeah, it wasn't the decking. The precast wasn't made composite as you would do now. It was so it was kind of just set on top of the girders, and I think there was always trouble even when they put it down getting it to be level because there's super elevation. It goes from tangent to super elevated across the bridge, and I think they always had trouble getting the panels because of across all 4 girders to sit right. That's the oral history I got.
Did the piers require any retrofits to provide support for the fixed bearings?
No, they didn't. I guess part of the problem is that's why we actually end up fixing 3 piers at Unit 2, but elsewhere it is the same fixity. We did have to go back to the older method to, PennDOT allows you to do that. So in some cases, we went back to the original method that was used to get it to work, and in some cases also we allowed a little bit of overstress. So
How tall were those piers?
I don't have the dimension, but they get pretty tall as you go over
Okay.
Clarissa Street. Let's see.
yeah, in that area they're probably around 30 feet or a little over 30 feet maybe.
Another question, did railroad restrictions have much an effect on the design other than the strong back system used?
I'll take that one. I'll say the design, no. Everything else about the project, a tremendous effect. Getting access to the property, even from the first time we went out to do inspection, we inspected the entire bridge and had to come back months later to get on SEPTA's property. And we had to get pretty much temporary construction easements for the contractor. Luckily, it was a yard, so access was right adjacent to the bridge, which was great for the contractor, but just getting the permission. But throughout construction, every submission from the underdeck shielding and everything is always later when it's over the railroad. It's just, you got to allow for that time in your schedule for railroad coordination.
Just to follow up on that, is there any lessons learned for during construction that you could have done differently in design, or it's just, it is what it is?
For the railroad part? I'd
Yeah, I
say
guess, would you have changed anything in design after going through construction
no.
to
If we,
eliminate some of those?
I think we knew that that strong back system was necessary. The railroad, there's no way you could do any type of jacking or any type of support from below for bearing replacement or pin and hanger replacement from SEPTA's property. The tracks are way, just no way you could do it. So that was always considered in the design. It's just what you have to account for in design and construction is just the time to get the agreements in place, the temporary construction agreements in place, and then in construction to get all your reviews done. And really what he got stuck in construction is he was getting like an hour to do some construction at night because there's a airport. This is all regional rail. The airport line goes through there. As he said, sometimes between the last train and the first train in the morning, they were getting like an hour when they should have got 4+ every night. So it's been a constant if you battle at construction.
All right. Anybody else have any more questions? If not, I'll turn it over to James to wrap it up.
Thank you. Do you see the slide of the glass of your hard-earned work right there? That's what everybody can receive if you present at SEI Philadelphia, this nice pint glass. But no, thank you, Joe and Asim, for that presentation. Excellent, very informative. So we'll get this pint glass out to you and a certificate of appreciation as soon as we can. We'll touch base with you on the best place to mail it or get it to you. But again, thank you very much. So our next meeting, our next technical meeting will be in April, and that's going to be part of the joint ASCE technical group session. That's usually held in April. I think tentatively it's scheduled for April 15th, but please keep your eyes out open for email blasts from ASC Philly on the time and date for the April meeting. We will have another meeting to round out the year in May. Again, keep an eye out for that. And then we won't have a meeting for March. Our March meeting is dedicated to College Day, which we try to, reach out to the college students who are looking to come into the profession within the next couple of years. So that's what we have to round out the rest of the year. I want to say thank you again for the presentation, and we'll see everybody in April.
Thank you. Thank you for this opportunity.
Thank you very much.
Thank you.
With that, I think we can all sign off, and we all get 15 minutes back to the hour. So
Thanks.
thank you.
Have a good one.
You too now.